The different orbitals have different shapes, and it will be important that we're able to visualize and draw the orbitals and understand what it is we're drawing. We start with the normal Cartesian axis system. In our system, the z-axis will be up and down, the y-axis left and right, and the x-axis front and back. For our purposes here, it really doesn't matter which direction is x, y, or z, and we may change the designations later. Now, s orbitals are spherical. If we draw one, the orbital looks like a circle. But we can make it look more like a sphere by putting in the z-axis poking out the top and bottom, and the y-axis left and right, and the x-axis out the front and out the back. The three axes meet at the nucleus, which in our drawing we can't see. It's important to note that when we draw a sphere, we don't mean to say that the orbital is a hard shell, or that it is a solid sphere like a billiard ball. Sometimes it is referred to as an electron cloud. For a 1s orbital, the cloud is denser closer to the nucleus and gets more diffuse farther away from the nucleus. As we go from 1s to 2s to the 3s orbital, the size increases. As the n quantum number gets larger, the orbitals get bigger. This was the same as was observed in the Bohr orbit model, where on going from n equal 1 to n equal 2 to n equal 3, the radius of the orbit got larger. There are 3 orbitals in each level with the label p, and these p orbitals lie along the 3 axes. The p sub z orbital is drawn along the z-axis. It looks like a figure 8 or a snowman. Again, we can make it look more three-dimensional if we put in the axes. The z-axis pokes out the top and the bottom. The y-axis is left-right, and the x-axis is front and back. Again, in our drawing, the electron cloud hides part of the axes. Let's remember what the picture is telling us. The electron is not a little ball that moves around in a figure 8 shape over the surface of the orbital. Much like the rope in our rope demonstration, the electron is stretched out into a wave shape and allowed to evolve over time. The drawing represents the three-dimensional shape through which the wave moves. The py orbital lies along the y-axis. Again, we can put in the axes. The y-axis left and right, z-axis up and down, and the x-axis front and back. We say the orbital has 2 lobes, one in the positive y direction and the other in the negative y direction. The p sub x axis, orbital is the hardest one to draw. Unlike a painting where you would draw the background first, with this orbital you should draw the lobe in front first, and then draw what you can see of the back lobe behind it. Finally, put in the axes. Front, back, top, bottom, left, right. Actually, that is not the final detail on these orbitals. We're going to shade in one of the 2 lobes on each orbital. Don't be confused. The shading has nothing to do with charge. This is a negatively charged electron everywhere. Nor does it have anything to do with electron spin. The wave of a single electron is stretched out through both lobes of an orbital. Two electrons with opposite spin both fill the entire orbital. The only thing the shading is indicating is the sign of the mathematical function. This will become important to us when we want to talk about bonding and add two of these mathematical functions together. But for now, just remember to shade one of the two lobes of a p orbital. It doesn't matter which one. One thing to notice about our orbitals is that an s orbital has the same mathematical sign, shown by the same shading, in every direction at any angle. In later courses, when you look at these orbitals in more detail, there may be changes in the sign of the function down inside the orbital, but looking from the outside as we do, the sign is the same in every direction. With p orbitals, the sign of the function changes. In these pictures from the internet, the lobes are not shaded differently, as we would do, but the planes which separate the lobes are shown. This is where the function changes from positive to negative and thus equals 0. We call this a node. For pz, this occurs at 90 degrees away from the z-axis. So this planar node is also referred to as an angular node, or a nodal plane. Above the py orbital, we add what appears to be a sine wave. But if you recall the rope demo at the beginning of this module, it is meant to represent the rope when there were two loops. Whatever the sign is on one side of the center, the sign is opposite on the other side, and 0 in the middle. Where it is 0 represents the node. You may think that these orbitals are easy to draw. I urge you to practice drawing them with the axes and the shading. It may take several tries to get them to look good. It's important that we be able to visualize these regions in space because when we think about sharing electrons in a bond, it is how these mathematical functions add together that dictates the bonding.